is very weird. So we're happy today to have Bharat Ratra visiting. Bharat got his PhD from Stanford, and he's a fellow of the American Physical Society, American Astronomical Society, and recently was awarded the APS Lillifeld Prize. I think what, last year?
Yeah.
Yeah, last year. And he's one of the originators of the whole idea behind quintessence and dark energy in a couple of really seminal papers with Jim Peebles. And so he'll be telling us about recent things on dark energy today.
Thank you, Keith. It's great to be back here again. I don't remember when I came last, but it was probably a decade or so ago. But before I start, I just want to point out this website. It's got some really clear videos on global warming that you might want to share with friends who might be interested in it. So we're doing cosmology now because there's a lot of really great data coming in. And this is reinforcing two really striking results. One's that we don't understand 95% of the stuff in the universe at the present time. And the other is that probably either quantum mechanics or relativity or both have to be modified. And that's the issue with the cosmological constant. And I'm going to just start with the review of the energy budget at the present time. So if there are questions, I'm happy to have them anytime in the talk. It might be better that way.
What did you mean by quantum mechanics has to be modified?
So we know
we don't normally modify quantum mechanics.
It's got to be extended.
Theory, right?
It's got to be extended to
in a non-linear way.
It's kind of unclear how you do this, right? So what we know is that if you go and calculate the vacuum point energy, 0 point energy, and just cut it off at the Planck scale, you end up with 10 to the 120 times the cosmological constant that's observed. Okay. So it's either GR doesn't really care about that, or quantum mechanics doesn't give you that. And I mean, this is kind of the biggest issue with quantum mechanics and GR when you put them together. And we have
people don't talk about changing quantum mechanics; they just say fine tuning. Yeah, just string theory. You don't need to.
Yeah, but so string theory doesn't really help you, right? So if you break supersymmetry, you're going to get a cosmological constant.
That has a landscape.
Okay.
I agree with that, but it's just fine tuning. It's just fine.
It's fine tuning, right? But
quantum mechanics as a construct is not changed.
It's probably either that or, I mean, so I don't know how you want to phrase it, right? So right now, quantum mechanics and GR are incompatible.
Well, I don't know why you would say it's incompatible. There's the cosmological constant problem, which requires a high degree of fine tuning, which we're not comfortable with.
Right. So you can phrase it that way, but it could also be that. I mean, so if you kind of think, well, maybe we can talk about this after the talk. Okay. Okay. So, so at the present time, we know that 5% of the energy budget is in atoms and molecules and a few charged particles, and we've known this for a while, but this number started getting pinned down in the 1960s. And even before that, Zwicky, looking at motions of galaxies and clusters, figured out they were moving too fast to have that motion caused by shiny stuff. And so you're seeing something dark. So he did not know that this number was only 5%. So he didn't know that what he was seeing was not made up of atoms and molecules, but it's pretty slowly moving stuff. So it's non-relativistic or cold dark matter. And more recently, we've come up with something called dark energy, which if you think about it in terms of a field and the mass of a particle, it's going to be moving very, very fast. It's comparable speed to the speed of light. because the mass scale there is 10 to the minus 32, 10 to the minus 33 eV. And it's also not atoms and molecules. And so basically, we don't understand 95% of the stuff out there other than seeing its gravitational effects. So what I want to do is motivate dark energy and then look at two physical models that are consistent, physically consistent. There's the standard model where you have a cosmological constant, and you can turn that into a scalar field with the potential. And I'm going to call that phi CDM. But that's kind of a messy model to work with and analyze data with. So people who do data analysis use fluid models for the dark energy, and they call it W or XCDM or W naught WACDM, where you have an equation of state and a pressure and an energy density for the fluid and the cold dark matter. And these guys, we'll talk more about that. They're not physically consistent, and you have to modify them to make them physically consistent. So I'm going to look at these models, and they make predictions, and those predictions depend on parameters of the models. And so you can compare to observations, and then you can constrain the parameters of the models. And that's usually called the classical cosmological tests. And we can get constraints on the parameters and see if the constraints from different data sets agree or not, and do a lot of stuff that way. And then I'm going to transition and look at the transition between deceleration of the cosmological expansion that happens earlier on when you're dominated by matter to the acceleration that happens probably when the universe was half of its current age, and talk a little bit about the value of the Hubble constant and measuring the geometry of spatial hypersurfaces, because the Planck data seems to suggest it's curved if you look at the data from just the CMB. And then I'll talk a little bit about another issue with the Planck data. So this is the PR3 data release. It seems to be giving you spectra of the microwave background that's a little bit excessively smooth compared to what you would predict in the best fit model. And there's some indication that that might be coming from excess lensing, but it's not clear what's happening. And then I'll look at the most recent DESI results in the last year or two, where they seem to find dark energy dynamics as favored over a cosmological constant at maybe 2.5 or 3 sigma. So we have lots of great data now, but we're not at the level where you can do particle physics like constraints. You can't do model independent constraints using cosmological data. And so what you can do is choose a physical model and parameterize that model with 6 or 7 or 8 and even maybe 9 parameters and get fairly tight limits on those parameters. And then you can play around by looking at whether you draw the same physical conclusions if you use different cosmological models to analyze the data. And you can analyze the same cosmological model using different data sets and see if the constraints you get from different data are consistent. And if they are, then you can do joint analysis. So there's a lot that we can do, but we're not able to get model-independent constraints from these data, except for a couple of very, very special things like the temperature of the CMB, but not for ordinary cosmology stuff. So we start with Hubble's law, which tells us that the recession speed of a galaxy is proportional to its distance. And this constant of proportionality is the Hubble constant. And astronomers have different values for the Hubble constant. This is my favorite value now, and I'll explain this in a little more detail. Sometimes in the past, when these error bars were much, much bigger and this number was more uncertain, people didn't want to pick a specific number to work with at the beginning of the computation. So they would write the Hubble constant as 100 times small h, and small h was a parameter that you could set at the end of your computation. So this is a typical data set. It's a really famous one. It's from the last paper of the Hubble Space Telescope Key Project on the Hubble constant that was led by Wendy Friedman. And this is from their 2001 paper. And these this axis is the recession speeds, the galaxies, and the distances are here. The units and numbers are down here. And this solid red line was the best fit then. And in that same year, Rich Gott, Michael Vogley, and a graduate student of mine, Sylvia Purariu, and I wrote a paper on the Hubble constant. And what we did is we went to John Hooker's webpage where he listed all measurements up to that point, and there were 270 odd measurements. And we just made a histogram of those measurements. And we saw that that histogram was very, very, very non-Gaussian. So if you have 270 measurements of a quantity and you're not getting something close to a Gaussian, that immediately tells you that the error bars of the measurements are incorrect. And so we just discarded those error bars and used median statistics that just uses the central values of all those measurements to do an analysis. And I'll give you the number from a paper 10 years later when we had 553 measurements. And we got 68 plus or minus 2.8. And that plus or minus 2.8 is mostly the systematic error. The statistical error is less than plus or minus 1. And the way we can estimate the systematic error is to split this 553 measurement data set into every individual technique they have. And there's enough, there were about a dozen or so individual techniques where we could do the data analysis for, again, using median statistics. And the scatter between the medians in those individual techniques gives you the systematic errors, and that's where we get this plus or minus 2.8. And this agrees with most measurements of the Hubble constant, with a few exceptions. It agrees with the WMAP measurements. It agrees with the Planck measurements. It agrees with BAO measurements. It agrees with Hubble parameter measurements. And I'll talk about this in more detail soon, but this is my favorite value of the Hubble constant. There's some controversy because some measurements give you a significantly higher number. And that comes from calibrating using Cepheid variable stars nearby and finding type 1a supernovae in those galaxies, and then getting into the Hubble flow using the type 1a supernovae. And this is from 10 years ago. More recently, this has come down to about 73 plus or minus 1. And this number is 68 plus or minus 2.8. So I want to compare these two. And so what I'm going to do is I'm going to use those as Gaussian priors in my data analysis. And the data I'm going to look at are large-scale CMB anisotropies, smaller-scale CMB anisotropies, and galaxy clustering data. And I'm going to do this in an extension of the ΛCDM model. So the ΛCDM model has 6 free parameters. And I'm going to add one extra free parameter, which is the number of relativistic degrees of freedom that are not photons. So these are usually what people call neutrinos. And in the standard model of particle physics, because the way things decouple, you have 3.045 neutrinos, and that's the dashed line over here. So what I've done here is taken that 7-parameter model and marginalized, after fitting to the data, marginalized over 5 of those parameters. And I'm showing you the likelihood as a function of Hubble constant and the number of effective degrees of freedom that are not photons, relativistic degrees of freedom. And I've used these as priors in the analysis. So the blue contours come with these priors, the red contours come with these priors. And you can see that the blue contours are very consistent with what you expect from the standard model of particle physics of 3 neutrino species. The red ones are about 2 sigma away, and things have tightened up now, so this discrepancy isn't that big. But one way of explaining this 10, 12 years ago, or maybe 15 now, was to say that there was one extra relativistic degree of freedom. And that's why you're getting a larger Hubble constant now, because you could change the expansion rate to allow for that. But
so could you do that with that? Could you remind me again, what is the CMB value of H0? Because that's much more precise.
So CMB value is about 67.5 plus or minus a half.
Okay.
And I'll come to that in more detail in a second. I mean, not in a second, in half an hour.
What about the Z decaying to a relativistic light neutrino? It can't do that, right?
It can't do that. So they make it a sterile neutrino, so it doesn't couple.
But then it contributes to ineffective.
Yeah, it contributes to ineffective because it's another relativistic degree of freedom, and you want to change the expansion rate by adding that.
Then you screw up BBN.
Yeah, you screw up BBN, yeah.
So you're moving one problem to another.
Right.
But the supernova, you can still get the supernova value of H naught with not allowing N effective to vary.
Right, you can get that other ways.
I thought it's still about the same, about 72.
So right now it's about 73 plus or minus 1, so it's become really tough. But
then I don't understand the red contour. Is the red contour?
The red contour is for this number, which is from 2011.
Okay, but you would get about the same number even if N effective was 3, right?
For the
supernova. So the supernova.
So these H naughts don't depend on N effective. So I'm just showing you the likelihood as a function of N effective. And
yeah, but the likelihood there, the red contour is the likelihood. It misses N effective of 3 completely. So that's
right,
what I don't understand.
Right. Yeah, it misses. This was happening 10 years ago.
Oh.
So now it doesn't, and now it's like about a quarter or maybe half an N effective. But like you said, for Big Bang nuclear synthesis, probably still rule that out.
Yeah, the limit's about 3.1 or 3.2.
Yeah, so it's somewhere right around there. Yeah.
Does dark radiation affect the local Hubble or not?
So it's affecting stuff earlier on. And so you can get it consistent with the CMB. So you can get the CMB and this guy consistent because earlier on your CMB value would be around here, somewhere around here, 73, 74.
So H naught from CMB will be definitely affected by the dark radiation, but
right.
How in local Hubble?
The local Hubble value won't be affected if it's just kind of a neutrino that has a mass that then becomes non-relativistic or close to non-relativistic now.
But then why do we see the red contour is moving to the right compared to the blue?
Because I mean that's it's not moving to the right. That's where it is, and you can say that it's picking up N effective. And picking up one extra N effective to reconcile it with the low value if you just go to the CMB.
Oh, that's so the red contours are trying to reconcile it with the CMB.
Right, because that's the CMB data in here.
Okay.
So if you want to fit the CMB data, you need one extra relativistic degree of freedom.
Right.
Okay, so we have an expanding universe, and we have to be a little bit careful because they're privileged observers, and those are the guys that rest with respect to the observations. And these are the guys who see everything isotropic on large scales. And if more than one observer separated in space sees isotropy, that means you have a spatially homogeneous universe. And that makes our life much simpler. It just allows you these 3 spatial geometries if you ignore the topology, and I can't draw them in 3 dimensions, so I'm showing you them in 2 dimensions. And you can have the positively curved sphere, the surface of the sphere, the flat plane. It's got to go out to infinity. Otherwise, you could go over here and look out, and it'd be anisotropic. It'd look different when you're looking in and out. So 0 curvature and negative, the saddle-shaped one. And that's the line element up there. And so we need equations of motion, and very loosely you can kind of think of the radius of this guy as your scale factor, and the dynamical variable is A, the scale factor up there. And these are the equations you get if you assume a fluid is powering this expansion. So the dot is the time derivative, and this is expansion rate contribution to the energy. And G is Newton's big G. This is mass, energy per unit volume of whatever gas you have. And you get contributions from space curvature and a possible cosmological constant. And you don't know how this changes with time, so you need an equation for that. And that's the first law from thermodynamics. And that relates the rate of change of the energy density to the pressure. And to complete this, you need an equation of state. So we know things are moving away from us, so stuff is redshifted. And that tells you A dot over A is positive. And you might be interested in the next derivative, the A double dot derivative, and that's pretty straightforward to get an equation for. You just differentiate this and do a little bit of calculus, and you get this equation here, where M now is the cold dark matter and the baryonic matter, and there's the cosmological constant. And I'm not using natural units. If I put back the c squareds, there'd be c squareds in the denominators of these terms. So those guys are relativistic effects. And if we just concentrate on ordinary matter, because of this minus sign, you get decelerated expansion. And if the galaxies are moving or whatever's contributing to the fluid, if they're moving, then you get non-zero pressure. And that gives you even more deceleration. So you have a problem if astronomers tell you that you have accelerated expansion. And there are two options. One is that Einstein was wrong and GR is not the correct model for cosmology. But if you're a little bit more conservative, you might want to take advantage of the fact that you could add in anything on the right-hand side into T mu nu in GR, because GR just tells you the geometry part of it. And you can add a cosmological constant, so we can go ahead and do that. And we can choose this equation of state. And if we make this choice, then this guy is going to be -2 rho lambda. And if you make rho lambda significantly bigger than rho matter, the negative part here is going to overwhelm the positive part, and everything inside the square parentheses will be negative, and that'll cancel that sign, and you'll get accelerated expansion. And that's why we have dark energy. It would be really stupid to do this if it was just one measurement we're trying to fix by introducing one new hypothetical substance. But there's about half a dozen different measurements of dark energy, and they all roughly agree. And so maybe we're on the right track. And we do have evidence for an equation of state like this in the lab that's associated with 0-point fluctuations. So you can look at the Casimir effect or the Lamb shift, and they're all consistent with something like this. And the hope is that on very, very large scales, quantum mechanics does something similar. So I had this parameter, which I didn't point out, this omega parameter. It's a density parameter in a strange set of units. So this is critical omega, this is underdense, this is overdense. And omega naught is just defined in terms of the energy density, the critical energy density that corresponds to a model where that is 0 and that's 0. Then you can get rho in terms of G and in terms of the Hubble constant. And that's the expression for rho. And it's about 10 to the minus 29 grams per cubic centimeter. And to avoid carrying that around, everybody gives you the ratio of whatever energy density you're interested in to the critical energy density, and that's what omega is. Okay, so dark energy was first discovered through a cartoon-like explanation of how dark energy was discovered. So we look at two different models, one that expands more slowly compared to one that expands more rapidly, and this is the Hubble relation in both those models. And so if you go to a galaxy the same distance away in these models, then in the more slowly expanding one, the recession speed is smaller than the more rapidly expanding one. So as you go back in time, you're going to look at stuff that's earlier and earlier because it takes longer for that light to reach you. And so you can measure the expansion rate if you can measure it as a function of time if you can see bright enough objects in the past that you can observe now. And there are three options. It could be that the expansion rate is constant and you just had a straight line like the purple line. Or it could be in the past that the expansion rate was more slow than it is now. And so you have accelerated expansion as you come to the present. Or you could have the opposite. You have decelerated expansion. And in the mid-1990s, the objects you could use for this were the type 1a supernovae. And most of them ended up in the blue part of the diagram. So this is what we have, that you have it more slowly expanding in the past, and as you come to the present, it accelerates. And you've probably all seen plots like this that give you the likelihood from the supernovae in this plane where you have omega lambda and omega matter. and this is cold dark matter and baryonic matter. So if you had no dark energy, your data should lie on this line at 0 omega lambda, and it doesn't do that. It's up here. And this was about 3 sigma, almost 3 sigma away from, a little bit less than 3 sigma. But this is from 20 years ago. And now just from the supernovae alone, you can get this at maybe 4.5 sigma or so, and that's just the supernovae. So we know that there's dark energy there. We also know it's the most significant contributor to the current energy budget, but we don't know whether it's a cosmological constant or whether it varies in space and time. And we can make a couple of assumptions that GR is correct, and so it's not a problem with GR, and we can assume that the astronomers are perfect and they have all their systematics under control. And then it's pretty straightforward to study this issue. You just take models, make predictions, and compare those predictions to observations. And this is the standard model. I'm going to show it to you at later time. So I'm not going to show you the photons because they're not important now. I'm going to plot the energy budget, energy contribution on this axis, and the scale factor on this axis, and it's log. And this is the baby universe over here, and we live over here now. And there's 3 lines here. They correspond to the matter density, which goes like 1 over a cubed. It's 1 over the volume, and that's the blue line. And then space curvature goes like 1 over a squared. Space curvature, goes like 1 over a squared. That's the orange line. And the cosmological constant is horizontal because it doesn't change with scale factor or time. So we have a constraint, and I'll show you this in a bit. But I mean, although it appears that you have 3 free things you can adjust, you cannot do that. And only 2 of these are independent. And we're going to choose omega matter at the present epoch as one parameter, and the other is omega lambda. And you can kind of see the immediate problem with a cosmological constant. This is energy per unit volume. So if you put this into natural units, it's energy to the 4th power. And if you take the 4th root of that quantity, what you get is about a milli-electron volt. So the energy scale associated with this green line is a milli-electron volt or so. And when this first showed up in the late 1990s, people always knew there could be a cosmological constant, but they rejected it because that was the energy scale associated with it. And that's not a fundamental energy scale. That's chemistry, right? So particle physicists don't like a new fundamental scale at that level. And in the last decade and a half, maybe this can be tied to neutrino masses, but I haven't seen a very convincing model for that. There's a very easy way to get rid of this energy scale. All you've got to do is tilt the line a tiny bit. And because the universe is so old, you can go back in the past and choose your fundamental energy scale to be 10 to the 9 GeV or whatever you want, and let that drop as time goes on. And your fundamental energy scale then reduces to a milli-electron volt now. And that's what the W or ΛCDM parameterization does. It just tilts the green line. And I'm going to drop spatial curvature for now to make these a little bit simpler. So we have ordinary matter, the blue line, and then this green line where you choose an equation of state P equal to W sub x times rho for the dark energy from this fluid. And if W sub x is less than -1/3, you'll get accelerated expansion. So when this starts dominating, you get accelerated expansion. As you go back into the matter epoch, it's pressureless, so you won't get accelerated expansion. You'll get decelerated expansion. And in this parameterization, I'm going to choose omega matter now and W sub x as my 2 free parameters. And you can see immediately what the problem is with this guy, because the speed of sound squared is dpd rho. And if W sub x is negative, dpd rho is going to be negative, and the speed of sound is going to be imaginary. So you'll get exponentially rapidly growing perturbations that make this universe very, very inhomogeneous. And so what people say is that we're trying to model dark energy, And the obvious model for dark energy is a scalar field. And in a scalar field, the mass scale is 10 to the minus 33 electron volts. And obviously, those particles are going to be moving at close to the speed of light. So let's arbitrarily set CS squared equal to 1. And that's how we're going to do the computations. But this is not a physical model. So what you can do is you can turn it into a physical model by taking a scalar field and getting an energy density for that scalar field. That's phi dot squared, the kinetic energy. And this is the potential energy density. And I'm choosing an inverse power law scalar field, potential energy density. And that's going to contribute to the Friedmann equation. You get the usual blue line over here. And because this is a new dynamical degree of freedom, you have to solve the Klein-Gordon equation also, and you have to do this numerically. And what you find is a changing green line. It's not a straight line, it's a curve. And this curve is really interesting because it's an attractor solution, and you can show this no matter whether you're in the matter-dominated epoch or the radiation-dominated epoch. And what it wants to do is if it starts out subdominant, if the green line is below the blue line, then the green line always wants to come to dominate. And this can explain partially the coincidence problem. So no matter where you start, the green line is going to want to dominate your energy density budget. And maybe that's a way to partially resolve the coincidence problem.
So why do you say partially?
Because it depends whether you actually have enough time to get this to work, right? So it depends on how much that green line changes as a function of time.
Move it up.
Yeah. And if you can get it to be big enough, then maybe you can explain the coincidence problem that way. But it still has the cosmological constant problem because there's going to be 0-point fluctuations that are going to add to this huge number. And the parameters I'm going to use omega matter now in alpha, where alpha is this guy. And I've chosen this inverse power potential energy density because of the attractor solution. And so I want to show you how you can constrain these parameters. And I'm going to use older data because the error bars are bigger. And we'll come back and look at the newest data in a second. So type 1a supernovae apparent magnitudes is a function of redshift, the baryon acoustic oscillation peak, and the Hubble parameter is a function of redshift, and growth factor is a function of redshift. And I want to give you a little idea of how we do this. So we want to work in terms of redshift instead of scale factor. So we rewrite the Friedmann equation in terms of redshift. And this is for the standard ΛCDM model. So instead of the 1/a cubed for dark matter and baryonic matter, you have 1 plus z cubed and 1 plus z squared for the curvature and no z for the lambda. And you can see immediately that if you choose to look at this equation at z equal to 0, this becomes h naught squared, and those two guys cancel. That becomes 1, that becomes 1, and you get the sum rule. So this always has to hold. So there's only 2 free parameters, because if you adjust 2 of them, the third one's determined. And that's why we choose, this is a conventional choice. These 2 are the conventionally chosen ones. And so in terms of these parameters, you can make predictions for the expansion rate at whatever redshift you're interested in. And those predictions depend on these 2 guys. And it also depends on h naught, because h naught shows up in front here. And this E of Z and P is just whatever's in the square parentheses here. You take the square root of that. So you can make a prediction, and then you can compare that prediction to your observations. And if you have 30 or 40 measurements of H at different Z's, you can write down however you want to do this, least squares of maximum likelihood, and get constraints. And the constraints are contours in parameter space. And so I'm going to show you a whole bunch of pictures like this. So there's going to be lambda CDM here, X or W CDM here, and phi CDM here. On the x-axis, we have omega matter for all of them. On the y-axis, you have the other parameter. This is omega lambda. This is W sub x, and this is alpha. And there's a bunch of lines. So the dashed line here is the zero curvature line. So models in this part of parameter space are closed like a sphere, and this part of parameter space, they're open, the hyperbolic geometry for space. The dashed line here is the flat lambda CDM model. So it's lambda CDM because omega sub x is equal to -1. So px is equal to minus rho x. And over here, the flat lambda CDM model lies at alpha equal to 0. So a model here at omega, say, matter of 0.3 is identical to a model here at the same omega, and it's identical to the same model over here on this dashed line. So that's where these spaces all they join together, they're consistent with each other. And there's small lines here. The dotted line here divides you between currently accelerated expansion, currently decelerated expansion. And the same thing's true here, accelerated expansion, decelerated, accelerated expansion, decelerated. And I'm looking at an older set of type 1a supernovae data, and they give you contours. So 1 sigma, 2 sigma, 3 sigma, and that's the best fit. 1 sigma, 2 sigma, 3 sigma, and best fit. 1 sigma, 2 sigma, 3 sigma, and best fit. So there's a lot of things you can conclude from this graph. So the first thing is that most of the data likelihood probability lies in the accelerated part of parameter space, and that doesn't matter no matter what model you use for the analysis. So you get accelerated expansion independent of what cosmological model you use for the analysis. The standard model with omega matter of 0.3, omega lambda of 0.7, and spatially flat is pretty close to the best fit point in each of these cases. And there's lots of room for space curvature. There's lots of room for dynamical dark energy. So we can move on to the next data set. Yeah.
Could you remind me again what the alpha was? It was in
So alpha is this guy.
Yeah, it was in the potential, right?
Yeah.
So alpha of 0 is just a constant.
Yeah.
Is it very different if you use an exponential?
For the dark energy. So the attractor solution you get there, if you solve this in a matter-dominated epoch, it wants to parallel the matter energy density. If you solve it in a radiation-dominated epoch, it wants to parallel the radiation energy density. So it never wants to do this. So it would be exactly parallel to the blue line. The green line would be parallel to it. So it doesn't want to intercept the blue line. And so it doesn't want to come to dominate. And I mean, we looked at a whole bunch of different potential energy densities, and this was the only one that worked that well.
How much does it depend on the initial conditions?
So which one? The exponential and the inverse parallel?
Yeah.
They're both independent of initial conditions because they're both attractor solutions, and you can show that they're attractor solutions analytically. And so they don't depend on the initial conditions. I mean, I don't know how far you can go globally out from those initial conditions that give you those attractor solutions, but they're pretty large part of parameter space is going to be drawn to it.
Sorry, so if I understood you correctly, you said that the inverse parallel is what partially solves the coincidence problem, while this exponential potential doesn't.
I mean, not if you just take a Klein-Gordon field, so just the usual kinetic g mu nu, d mu phi, d nu phi, v, and just adjust your v of phi, and you're coupling it to Einstein gravity. So the exponential potential doesn't solve this because the solution, and you can just work this out analytically, the solution there is exactly parallel to the blue line, and you can do this in the radiation epoch, and it's exactly parallel to the radiation energy density. So let's go to baryon acoustic oscillations, and you get the same sort of things, except the really important thing is the orientation of these contours. So you can compare this to what you get for the type 1a. Sorry, that's going the wrong way. type 1a supernovae, and it's almost orthogonal. So you can see what happens when you start combining baryon acoustic oscillations with type 1a supernovae. You're going to be pushed to a much smaller region in parameter space. So all the conclusions I said about type 1a supernovae are true here. Most of the probabilities in the accelerated part of parameter space independent of the model. And the best fit model is pretty close to the standard model. And there's lots of room for space curvature, lots of room for dark energy dynamics. And it doesn't matter what data you look at. So this one's a little bit different. There's two sets of contours because one of the Hubble parameters we use is the Hubble constant. And so we've done it independently for this and for this. And you can see that they move the contours by about half a sigma or so, but they're both consistent with the standard model. And so this is a systematic that can affect your data analysis, and growth factors here. So the really important thing is that the constraints from the different sets of data are not inconsistent. And then you can look at it more closely. They're also consistent with the standard model with omega lambda of 0.7, omega matter of 0.3. But there's lots of room for time evolving dark energy and for spatial curvature. So the next thing to do is look at this two data sets at a time. And that tightens up the parameter space quite a lot. And the standard model is still pretty close to the best fit model. And there's room for some space curvature and some dark energy dynamics. And it doesn't matter what data set pairs you look at. So if you have the Hubble parameter, there's going to be two sets of contours because of the Hubble constant value. And so you can tighten things up when you do two data sets at a time. And the standard model fits them well. And there's room for dark energy dynamics and spatial curvature. And we started seeing different things. So we could see the difference between the Hubble constant values giving you a systematic. There are other systematics, different types of supernovae data, different combinations, different groups give you different constraints. I haven't shown you gamma ray burst data, but they do the same thing. And there's other parameters that go into this. So there's systematic effects. And I'll come back and look at the most recent data really soon. So before I do that, I want to look at a couple of digressions. So we can measure the Hubble parameter now, and this is again from 10 years ago when there were 28 or so measurements of the Hubble parameter as a function of redshift. Instead of plotting just h as a function of redshift, I divided h by 1 plus z because otherwise the line rises really steeply and you don't see the structure here. So these 6 models in here are the best fit models. So there's a two lambda CDMs, 2 X CDMs, 2 phi CDMs. And because H naught is one of the Hubble parameters, you can see 3 of them end up here and 3 of them end up with a lower value of H naught. And these 2 models are 3 sigma deviant models from these data. And so you can kind of see that these data have a dip. The models that fit these data have a dip, and it's somewhere in between just being completely flat here. And you can't see the data showing you that too well, but we have a dense enough set of measurements at low redshift, so I can bin these in redshift, and you can see what's happening a little bit more clearly. So these are now 2 sigma error bars, 1 sigma, 2 sigma. I can't do that at higher redshift because I don't have enough data there. It's not dense enough in redshift to bin it in redshift. But you can see that it comes in and then goes back up. And if you look at what the prediction is in lambda CDM at larger redshift, where z is larger, this is going to be the dominant term because that has a z in the denominator. So you're seeing the decelerated expansion as you come in, and then you go to lower and lower z, then this term is going to become more important relative to this term because this guy is a factor of 3 or so bigger than this. And you can see the transition over here to accelerated expansion. And so this is from 10, 15 years ago. So we're hoping from DESI to get maybe 100 of these points out to a redshift of about 3.5. And with much tighter error bars, you can see that these 6 best fit models are all consistent within 1 sigma with the measurements. But maybe when DESI comes along with their final data set, they'll be able to distinguish between these models. So I now want to go back to the best data we have now. I'm going to just avoid the DESI data for now. And I'm going to look at a combination of data sets like BAO that go up to a redshift of 2.3, Hubble parameter that goes to a redshift of 1.9, supernovae from the Pantheon Plus collaboration that goes to a redshift of 2.3. And almost all the statistical weight is in these 3 measurement sets. I'm also going to look at angular sizes of quasars that go to a redshift of 2.7 and reverberation mapped quasars, both the MG2 ones and the C4 ones. And I'll come back to that in a second and show you what I'm doing with those. But this goes to a redshift of 1.9, this goes to a redshift of 3.4. And there's correlated gamma ray burst data, in particular the Amati correlated ones that go to a redshift of 8.2. So I'm also using that. And I'm going to use these in a way that's completely independent of the CMB and it's completely independent of local calibrators. So I can do it completely independent of the CMB because I'm going to use omega baryons and omega cold dark matter as my free parameters instead of omega matter. And that allows me to actually take the model equations and compute the sound horizon at drag epoch, which I need to calibrate the BAO data. So if you have a model and you know omega baryons and you know omega CDM, all you have to do is an integral. And so I'm effectively measuring the sound horizon at drag epoch from these data. And if I do that and fit that through these 6 different models, you can see the Hubble parameter, Hubble constant values. They all have error bars of plus minus 2.4. And they range from 68.9 to 69.5 or so. So it's plus or minus 0.3. And if I call that plus or minus 0.3 my systematic error, and just take the average central value at 69.25, and I get 69.25 plus or minus 2.4. This is independent of the Cepheids, it's independent of any other local calibrator. It's independent of the value from the CMB because I'm not using the CMB here. And it's the value I get is quite consistent with the median statistics one. It's quite consistent with Wendy Friedman's value, which she gets using the tip of the red giant branch and then goes into the supernovae for the Hubble flow. And she's done James Webb and Hubble Space Telescope measurements of that. It's about 1.5 sigma below Adam Rees's calibrations using Cepheids and going into the Hubble flow with supernovae. And it's also consistent with the CMB value from Planck. So our flat lambda CDM model is about 0.9 sigma higher than the CMB, and it's about, depending on the model, it's between 1.3 and 1.6 sigma lower than this. And there is an interesting thing that needs to be done at low redshifts because these guys, they differ by about 1.2 sigma. But it would be really, really nice to see what's causing this difference, even though it doesn't seem that significant. But this becomes really, really important because if the error bars are really plus minus 1, and this is plus minus 0.5, and these differ by such a huge number in the central values, then you get a very significant result. But if the error bars is plus minus 2, and this number is not that different from this one, there's no issue about local calibrators and the CMB giving you different Hubble constants. And independent CMB experiments from smaller lengths, smaller angular scales from the Atacama Cosmology Telescope and the South Pole Telescope are quite consistent with all these numbers and this number. So that's the Hubble constant. The next thing I want to talk a little bit about is the space curvature, because Planck, if you analyze those data alone, just the CMB, it favors a closed geometry at maybe 1.5 sigma or so. But that goes away when you have BAO added to it or supernovae added to it. But they still assume a time-independent dark energy. And so maybe things change if you have dynamical dark energy. and try to look at this constraint again about closed geometry. And that's what I want to do first. I'll do that without the CMB. And if I have time, then I can go to the CMB. So I'm going to come back and put in space curvature in this dynamical dark energy parameterization. And I'll do the same with the scalar field. I'll put in the orange line and then go back to that data compilation. And maybe I should tell you a little bit more about this data compilation. So we looked at each pair of data sets individually before we combined these. And we looked at a bunch more data that we did not use. So one of them was X-ray UV calibrated QSOs, and we can show that those are not standard candles. We also looked at reverberation mapped H-beta QSOs, and we can show those are also not standard candles. And we looked at H2 starburst galaxies, and we can show those are not standard candles. So we didn't use these. And each of these data sets are mutually consistent, and we checked that before we combine them to get these joint analyses. And so if you measure spatial curvature, they are only between 0.4 and 1.2 sigma away from flat geometry. So there's a small signal there. It's not very significant, and the flat geometry seems to be quite okay. If you do dark energy dynamics, you get a deviation of about 2 sigma in favor of dynamical dark energy. And this is data from 2023 and 2024. It's pre-DESI. So other groups have seen this favoring of dark energy at 2 sigma level before DESI 2. And so it's Saul Perlmutter's group and the DES group at Fermilab with the supernovae they have. And I want to just digress again and look at how we can probably get new standardizable candles. So if we look at AGNs, there's a massive black hole at the center, and there's an accretion disk, and then there's what's called the broad line region and the narrow line region. So that's depends on the width of the line that you see that's being emitted by those regions. And so what's happening here is if you have some fluctuations in the emission from the black hole, that guy takes some time to get out over here electromagnetically and excite what's happening over here, and then you can detect that light that's being emitted. So if you can measure both in the ultraviolet from here and at the other wavelengths, depending on what line you're looking at, you can see those fluctuations, and they'll happen later over from the light from here compared to what happens with the black hole. So you know this stuff travels at the speed of light. So if you can detect those fluctuations, then you can measure the radius of the secretion disk. And it turns out that the radius or the time delay between the light from here and here is correlated quite well with the absolute luminosity. And this is an example with about 70, 85, 95 or so sources in the MG2 line. And this is a really, really good correlation. So we know that when we have different lines we can look at. So we have between 50 and 75 sources, and we see this correlation in all of them. And the interesting thing is the LSST observations at Rubin should get 10 to the 4 or 10 to the 5 such sources that can go all the way up to Z4 or even higher. And if we can have enough follow-up time to get the time delays, this relation holds for these new sources, then you have a new standard candle. So, how much time do I have?
About 10 minutes.
About 10 minutes, okay. So I haven't used the CMB anisotropy in the non-flat geometries, and I want to do that next. And we can't use the scale invariant spectrum because there's an extra scale here when you have a non-flat geometry. So in addition to the Hubble scale, you have the space curvature scale. And so Planck's analysis assumed a P of K when you should have really computed it from a closed or open inflation model. And they did not check that the fluctuation power spectrum they assumed could come from an inflation model, because the only way you can get a consistent power spectrum in these non-flat geometries is to use inflation. That's the case where it becomes really important, because you don't have a systematic way to get these power spectra other than inflation. So in the closed case, the eigenvalue of the spatial Laplacian is this, and capital A is discrete. It goes from 2, 3, 4, and so on. And the spatial harmonics are very different. So you do the fluctuation analysis, and then you say that on small scales in the conformally related space-time, where it's conformally equivalent to Minkowski space, that it gives you a simple harmonic oscillator initial conditions, also called a Bunch-Davies vacuum. And you can get power spectra. So if we assume a very, very slow roll inflation model, this is the power spectrum you get, and it's quite messy compared to that guy. And Q is related to this capital A, and capital K is the curvature in terms of H naught and omega K 0. So this was the only known power spectrum until the late 2018 or so, when Planck started using this, and I'll come back to the Planck one. It's untilted, and because it's very, very slow roll inflation, so it's equivalent to getting on small scales when you go to a large Q, a large K, or large A, you'll get back the scale invariant spectrum, and it's going to come back with an n equal to 1. And we know that that's completely ruled out even from the multiples, the 50 and higher multiples. You don't have to go to the really large angular scales where this has some effect, but just from the data of L of 50 and higher can rule this model out. And so what Planck did in the analysis was take the slow roll model and say they know at small angular scales it's going to give you n equal to 1. And we're just going to go ahead and multiply it by k to the n minus 1 to give you the tilted models they wanted for this power spectrum. And they didn't show you could get this out of an inflation model, but we're trying to finish up a paper now, Alan Guth and Mohammad Hussein Namju, on inflation models that give you a spectrum of this form. And unfortunately, I don't know how to say this, but Mohammad Hussein Namju is in Tehran, and we have lots and lots of problems communicating with him over the past year. So hopefully it'll get done in a while. But I've also computed an analytic power spectrum from inflation, and the formula is very, very messy. I'll just show you the matter power spectra. So this is the open case, this is the closed case. If we look at the open case, this is the standard flat ΛCDM Harrison-Peebles-Hughes-Oldovich spectrum, the correct power of n that fits these data. And this is the Planck spectrum they used in the open case, the dotted line. It goes up at large angular scales, at small k. And this is the analytic one I computed, which I'm calling the new PQ. And so you think there's a huge effect here, but the data are really poor at those angular scales. There's lots of cosmic variance, and so there's only a small effect. And so I want to show you the results we get from this, and I'm going to compare to the Planck data, the TT, TE, EE, and the low E map, as well as the gravitational lensing potential power spectrum data and BAO data. So there's 16 measurements, including 4 growth factor measurements from EBOS and individual growth factor measurements from velocity field measurements and type 1a supernovae apparent magnitude measurements and Hubble parameter measurements. And I'm going to constrain 12 different models. So there's going to be 3 different power spectra. There's the flat tilted power spectrum, the non-flat tilted one that Planck used, and the non-flat one that I computed analytically. So that leaves a factor of 4. So the 2 of that 4 is coming from ΛCDM versus XCDM, and that leads a factor of 2. And that too is coming from this parameter here, capital A sub L. So I'm going to analyze 6 of these models with capital A sub L set to unity. And I'll analyze the other 6 where I'm allowing capital A sub L to float. And what capital A sub L is, it's an amplitude parameter that rescales your input 2-point gravitational lensing potential contribution to the analysis. And you're kind of hoping that it comes back with A sub L equal to 1 plus minus a really tiny number. And that'll tell you that your best fit cosmological model gives you the right kind of gravitational lensing, smoothing of the CMB that you can see in the CMB data. But it's been known for some time that in the Planck PR3 data release, that it comes back about 2.5 sigma larger than 1. And some people have interpreted that as saying that you're missing some CMB lensing, but it's unclear if that's what's happening or there's some other systematic effect. This is not a physical model. This is just a consistency check parameter. So I'll start out with A sub L equal to 1 in the ΛCDM model. And there's 3 of them with the 3 different parameter, 3 different power spectra. And what I want to do first is compare the constraints that just come from the Planck data without lensing against what come from the non-CMB data. And you can see that they're consistent in the ΛCDM model, the spatially flat one, and they're about 2.5 sigma away from each other in the non-flat models. And my threshold for jointly analyzing these 2 data together is that they have to be consistent up to 3 sigma, because we're not perfect yet, and there's probably some systematic effects that we haven't quite understood. So if you compare what comes from P18 plus the lensing versus the non-CMB data, they're more consistent. So I'm going to just say that these guys are all consistent at my threshold, and I can analyze them together and measure omega curvature. So if I measure omega curvature for this, I get 0.009 plus or minus 0.0017. So that's half sigma away, and it's open geometry. And so I'm just going to conclude that it's quite consistent with flat spatial geometry. So now if I allow A sub L to float and just show you the more deviant combination here, those discrepancies become even smaller. And so it's fair to jointly analyze these. These guys also become smaller in this case, but I haven't got space to show you that. And so I'll do the same thing. I'll jointly analyze all these data and measure spatial curvature again. And I get tighter constraints on space curvature. But when I measure A sub L, it starts deviating by a factor of about 2.5 from the value you want, which is 1. And so it's consistent with flat geometry, but Planck PR3 is forcing you to say that there's something strange going on here because this is not consistent. So you can't really conclude much yet from these 2 guys, because by themselves, they have somewhat bigger error bars than the Planck data that are coming towards it now. But when you combine and jointly analyze them with Planck, Planck also dominates them and still gives you a deviation. Although if you just use them by themselves, they're consistent with A lambda equal to 1. And Planck data by itself in this new release, which wasn't completely analyzed by the group before they ended their being the Planck group, but some of the members then went on to analyze this PR4 release. They found A sub L more consistent with 1. So if I go back and look at ΛCDM and do the same thing with A sub L equal to 1, I find much more bigger deviations between the Planck data and the non-CMB, independent of whether I include or exclude the lensing. So what's happening here is the CMB data, in this case, wants to give you phantom dark energy dynamics. So it wants omega x to be smaller than -1, while the non-CMB data want omega sub x to be quintessence-like, to be greater, more positive than -1. And so those guys are too far apart to be jointly analyzed. So if you set A sub L equal to 1, you can rule out this dark energy dynamics parameterization. If you allow it to float, these guys come back down to below 3 sigma. And then I can measure a space curvature by jointly analyzing them. And you get a slightly stronger signal, about 3/4 of a sigma open. Dark energy dynamics is favored at about 1.5 sigma. And it's all quintessence like from the joint analysis. And A sub L comes back to be about 2.5 sigma greater than 1. And if have I run out of time?
Should wrap up. Yeah.
Okay, I can. Should I skip the DESI stuff then, or I can come back to that later if anybody's interested. Okay, so we don't know what the dark energy is, so we can fit these data with some mild dark energy, dynamical dark energy. And to do this analysis, it's really important to use physical dynamical dark energy models. So I think the universe is flat, but it would be really nice to understand theoretically these non-flat inflation models more carefully. We don't know whether this is a problem for the model or whether it's a problem with the data. And this seems to persist now, even in the PR4 data. We had a preprint out in archive earlier this week where we've done that analysis, and we don't know what the dark matter is. So after we understand all of this, cosmology is not going to be over. There's a lot left to do. And I can leave this up for a few seconds if people want to look at it. So even understanding all of dark energy and dark matter leaves a lot of issues. Thank you.
Remind me, what's the difference between the XCDM and phi CDM?
So XCDM is
One is omega x.
so one's a fluid model with this equation of state, and this line is a straight line. So phi CDM is a dynamical scalar field with a potential energy density, and you have to add the Klein-Gordon equation to the Friedman equation. So that's the model Peebles and I looked at.
And so I didn't, when you said that the XCDM was problematic
Yeah.
at the end, what about the phi CDM?
The phi CDM is not, because it's a physical model. It's coming from a Lagrangian. It'll give you a speed of sound that's consistent with what we expect.
The W never tends towards less than -1.
So this guy, if it's negative, then dp rho is negative, and CS squared is negative, and so CS is imaginary. And if you think about the gene's instability, that has an exponentially growing inhomogeneity, and so it makes things very, very inhomogeneous very rapidly, and it doesn't look like our universe at all. And so they want to do, so in the scale of...
But lambda CDM is included in this, right?
No, lambda CDM is not a problem because lambda CDM can't have fluctuations. So there's no inhomogeneities in the lambda value. So that's the one exception with the fluid model with at W sub x equal to -1, it's fine.
Yes, so I just have a question about this dynamical dark. I mean, it's not a surprise that these dynamical dark energy models, the scalar field is phi CDM, works because you introduce another parameter compared to the cosmological constant, like this alpha.
No, it's just one extra parameter. Yes, okay, yeah.
Yeah, so that extra parameter gives you wiggle room to match any inconsistencies with lambda CDM.
Yeah.
But then I would also say that for the DDE, this dynamical dark energy, you're making the problem much worse because with the cosmological constant, you just have to worry about the tuning of the cosmological constant. But then when you add in the dynamical dark energy, you still have the cosmological constant problem, but now you've added another problem, which is the tuning of the potential, because there are huge radiative corrections.
Right, but I mean, you have radiative corrections even for just the cosmological constant.
But what's the best model then with that you have? Say?
So, I mean, we can just say that there's this extra parameter, right? A cosmological constant, and call it a parameter, and say we're just trying to measure that, and we don't have any real idea of how to explain this. But in physics, the rest of physics, everything's given to you in terms of fields, right? You don't have anything that's a constant like that, unless it's a fundamental constant. And so if you think this is another field showing up as dark energy, then you want to introduce a field for it. And the simplest field you can use is a scalar field.
Yeah, but now if you introduce a field, don't you have to maintain the flatness of the potential? I mean, it seems like it's...
I mean, I don't see that that's very different than maintaining the cosmological constant.
Both now, because you still, even with the scalar field, you still have the possibility of using a constant. So you still have to...
Right, you can add a constant back, but you can add a constant, and that would be the vacuum energy, right?
I just meant that with a field, you still have to do the tuning of the CC, because with the field, you still have to cancel the electroweak vacuum energy, QCD vacuum energy.
Right.
But then with the scalar field, then on top of that, you also have to keep the quintessence field or whatever you have. You have to keep that flat as well. So it seems to make it, I mean, it just seems that it's just a bit harder.
Right. I mean, you can say it's more complicated that way. But if you think about this, right, so this is not something you can do the quantum mechanics of, and it's kind of supposed to be an effective field. Yeah. And I mean, you just don't know how to do the quantum mechanics of the potential of that.
But are there any models which try to tame the radiative correction?
So yeah, people have looked at this in scalar field models, and you get the same problems you get with just the cosmological constant. And I mean, maybe it's worse because you have to tune this whole field to give you what you want. But I mean, it's basically a problem putting together quantum mechanics in GR. And if you find this fits the data better, then you have a pretty big clue and you know how to look for it. And DESI is now seeing dark energy dynamics at maybe close to 3 sigma, maybe 2 3/4 sigma.
But I thought those results were, I don't know, I thought that those results were not accurate in the sense that when they were parameterizing it, they were parameterizing it over models, over phantom energy models, which they shouldn't have done that. Their prior should have only been W greater than -1. And if you do that, then
yeah, so if you do it with, so this is, I can show you compared to the first year DESI results. So this is what they find. So they use this model with these two parameters and for the equation of state. And you can see at low redshift, this guy goes away. So you become that. And at high redshift, this guy becomes just these two add together because that becomes unity. And so what they find is the CMB data, if you look at this plot, so at high redshift, that's the ΛCDM W you want, and at low redshift, that's the one you want. And the CMB data favor phantom-like energy, dark energy dynamics, and the non-CMB data are in the quintessence spot, and that's ΛCDM. And if you combine them and do a joint analysis, and you can because they differ by less than 3 sigma using our prescription, you get these blue contours. And these blue contours are 2 sigma away from the ΛCDM model. So the first thing I want to do is put back in the A sub L. And if you do that, the CMB data spread out now. And your blue contours are now consistent with they're just about 1.5 sigma away instead of 2 sigma. And you get A sub L back to be about 2.5 sigma away from 1. So maybe some of this evidence is coming from the excess smoothing of the Planck stuff. And you can see that there's a real effect here in the sense that it's not just the error bars that are larger. I mean, the error bars don't change when you introduce A sub L. The central values of those two things move closer together. the lambda CDM point and the center of the blue contours. And I've done this with the phi CDM model. We've done this with the phi CDM model. And we find quintessence like dark energy dynamics can fit these data. And it doesn't have to be a scalar field. And there's two other papers after this one that have found the same thing, that it doesn't have to have phantom-like behavior to fit these data.
Yeah, I guess one question. So at the very last part of your talk, you were telling us about your non-plan models.
Yeah.
Your computational R spectrum of non-plan models and the colloidal case. So they're consistent with the flatness of the universe. But aside from pure academic purposes, why is it important to know whether K is zero or it's not zero? Does it, for example, does it tell you some remarkable point in pre-inflationary era?
So I don't know if it does anything about the pre-inflationary era, but I think it's really important to know whether the spatial hypersurfaces are flat or they're positively curved.
Like, why is there any something that we can resolve if you have?
Well, I don't know if there's anything you can resolve, but it's going to be a fact about the universe, right? I mean, it's just like why are you interested in dynamical dark energy models? Because you want to see if the dark energy is varying with redshift, and then maybe you can go back and look at something else. But it's just a parameter of the universe, and you should try to measure it because it can be put into Einstein's equations. Just like cosmological constant could be put in Einstein's equations. But if you go back to the early 80s, after inflation came along, almost every theoretical particle physicist said it's obvious that omega matter has to be 1 because you can't have a cosmological constant because it gives you this energy scale. And space curvature doesn't make any sense because if you had flat geometry and you let it inflate, it would become even flatter. And some observers who were studying the measurements of omega matter knew for sure that omega matter was about 0.2 or 0.3, but lots of theorists just chose to ignore that. And so it was a surprise to a lot of theorists when the cosmological constant showed up 15 years later. Even though it was pretty clear. I mean, even when Jim Peebles and I were looking at these papers, writing these papers in 1987, at that point, that omega matter was 0.2 or 0.3, and so it had to be either cosmological constant or curvature.
Let's thank Bharat.
Thank you.
We'll see. If they part of the where they have lunch close to.
Okay, so this is on campus.
It's on campus.
Do you need a jacket?
I don't know.
So